Welcome to another tutorial of the thermal system design class. In previous tutorials, we solved for the problem 3, which was a flow through a pipe in the internal flow, and we solve it as a 2D analysis. So in this tutorial, we're gonna solve it in a 3D analysis. So first, we'll select Fluent. And we'll go to Design Modeler. First thing to do inside of Design Modeler, we select Units, change it to inches. We'll create a new sketch on the XY plane. We right click and we go to look at, we go to sketching, circle, select the origin. If we go to dimensions and we click on general, we can define the diameter for our circle, and we've created our 1-inch circle. We finish the sketch. And now we're gonna extrude it. Select the sketch. We'll just extrude it on the normal direction. The extrusion is 30 inch. And we'll click on generate. And that is our cylinder. So if we close this, we go to meshing. We're gonna create a meshing for we're gonna create a structure mesh and an inflation layer. So remember that we want a finer mesh at the walls of the cylinder, because that's where the point of interest for analysis. So the point of the inflation point is gonna help us apply our face mesh. We right click, insert, inflation. We'll click on our geometry, apply. Our boundary layer, we want the face around the cylinder. We apply it. We can do 10 minimum layers. We can generate our mesh. Notice that our mesh is on more tetrahedrons than on quadratic, so we'll go to meshing. Well, it's the element order is linear, so we're gonna change this to quadratic. We're gonna generate it again. And this is the result. So it did not change a lot. So we'll go with this one. So we can see here, if we go to the edge of the cylinder, if we go to the inlet, we can see the layers of the inflation. So that's gonna give us a more defined meshing around the boundary conditions or the walls. So next step and final step to do here on meshing is to name our faces. We click on here and we'll name this the inlet. This we will name it our outlet. And this is going to be our wall. You can see our name selections generated. Close our meshing. Notice that we still need to update it here on the interface of ANSYS. And once it's generated, we can go and create our case setup. We'll just leave it as a single precision. We click on start. So inside of Fluent, we'll check our meshing. So we check our minimum volume and we reassure that it's not equal to a negative number. So this means that our meshing is correct. We can report the quality. So we have not a very good quality on this example. We'll just keep on going with this one just for demonstration. We'll go to models. We'll turn on the energy equation. Our viscous, we know that this is a laminar flow. We go to our materials. On our fluid, we'll have to create edit. Go to Fluent database. We'll select water liquid. Copy. You can close this, change create. Close. We go to our cells condition. Notice that the material name is air, so we change it to water liquid. We apply. We go to our boundary conditions. We click on our inlet. This is the velocity inlet. We edit it. The velocity magnitude we calculated from last time. So it's 0.097 meters per second. And our thermal at the inlet water temperature is 353 kelvins. We apply it and we close. Our outlet we changed it to outflow. The flow rate weight is just 1. The temperature in our wall is room temperature, so we go to thermal conditions. We select temperature. We change this to 298. We apply it and we close. We can check our reference numbers at the inlet. Everything is right. We go to methods. We select scheme simple, least square cell base, pressure is standard, momentum and energy are second order upwind. Click on controls. Everything is, we leave it as default. For definitions, close our monitors. We check our residuals. Everything is right. We're not going to change our conversion criteria. We initialize. We'll run our calculations. We'll run 100 iterations. Calculate. So our continuity and velocity, it's reducing. So that's good because it means that it's gonna converge. Let's run 100 more iterations to see if it converges. Let's run 200 more. So it seems that that's as far as it's gonna go. Notice that you can change this temperature, and for example, if you go and change your temperature at the water inlet, you're gonna have a spike on your energy residual line. So it's something to consider. You can actually change and run another 100 iterations on a different with a different with different conditions, and it's gonna give you different solutions. So now that we run our calculations, we go to results, graphics, contours, and we're gonna create a new surface, isosurface. We're gonna select our mesh, computer. We can also change our units. Length, we'll change it to inches. We close this. We have our on our x coordinate normal to the x coordinate. We have these conditions. Let's say, for example, if we create, let's not display the wall. So you can see the plane that it created for our simulation. So it's right at the center, at the center of the cylinder. It's called x coordinates. So we'll create our contour line using this plane. Contours, velocity magnitude. Save and display. At our x coordinate 3. So this is our velocity throughout our pipe. Let's check our temperature, how it looks like. We can see that our temperature, how it's fully developing at the very end of the cylinder. And we can also go into plots, create an XY plot. We'll have to create a new surface. Let's create lines. So we know that on the Y direction, we have a 1 inch diameter, so it's going to be a 0.5 and a negative 0.5. There's nothing on our X direction, and on our C, remember that when we started at the origin and when we extruded from the outlet to the C direction. So this will be 0, 0 at this corner in the outlet, and this is gonna be 0, 30. So if we want to create 1 inch apart lines from the inlet of the cylinder, we'll select 29, we'll create, select 28, create, 27, create, 26, create, and 25. So we created lines 1 inch apart. If we go to our display, we can see where the lines are. So we can now create the plots. So if we close this, we change the direction to 1. Let's say we want to see our velocity. From last time, we know that we'll position it on the y-axis. Velocity. Line 1, 2, 3. Let's plot them all together, and we can see how the velocity is developing the more that we move down the stream. So we see the first one. So compared to our 2D problem, we can see that our velocity is developing a little bit sooner, and it's not becoming more quadratic as we go. It's definitely can be also some errors. So most of the time, we will in this type of problems, as we can see, the 2D analysis gave us a very accurate representation of the problem. So sometimes we want to take the 2D instead of the 3D just to save time and computer space. So that's definitely something to consider. So in future tutorials, we will work on different case studies.